Yeah. Well, let me just point out, how about this? If I have, I'm just gonna state it. There's got to be a better way to argue here, but check this out, right? If I want to calculate the inverse map of C1 through Cn, what's that? That's, you know what that's going to be, right? That's going to be the sum, I equals 1 to n, of what? C, I, Vi, right? In other words, the inverse map, it takes the standard basis and it maps it back to the abstract basis. That's what defines the inverse coordinate map. So it takes the coordinate, the column vector, and it strings it out as the coefficients to the linear combination in the abstract. I mean, that's what the coordinate map does. And of course, you can prove that that is a genuine inverse for beta, right? If you compose one with the other, you get back where you started, in either order, fine. I feel like there's more I should be saying here, but I can't think of it at the moment. Let's look at an example, okay? So, how, yeah?
We're saying there's an isomorphism between the coordinates given by the standard basis and the coordinates given by any other basis.
I'm saying that for a vector space, the coordinate map defines an isomorphism from the given vector space to Fn.
Okay.
Yeah. But the inverse map, of course, it also defines an isomorphism from Fn back to the vector space, true. Because a linear map, which is invertible, has a linear inverse.
Okay.
So, yeah.
That makes sense.
Another nice thing about linear algebra. Other contexts, just because you have a function from one topological space to another, and f is continuous. Is the inverse automatically continuous? No. If it's an open map, sure, but not generally. Linear algebra, if you have, if you have a bijection from one vector space to another, it's automatically, like if the bijection is linear one way, it has to be linear the other way. Yeah. All right. Don't ask me for a nonlinear bijection. there might be such a thing. All right, let me not think about that in the remaining 5 minutes here. An example. We should do an example. So, how about this? Let's look at our 3 by 3. All right, that's my that's a vector space, right? 3 by 3 matrices. And I want to point out that you can take any matrix, right, A, and you can write it as the sum of a symmetric and an anti-symmetric matrix. See, this A is actually the sum of 1/2 of A plus A transpose plus 1/2 of A minus A transpose. You can prove symmetric, anti-symmetric. All right? Okay, fine. Let's define L going from R3 by 3 to R3 by 3 by L of A equal to, I don't know, A minus A transpose. You can check. L is a linear transformation because the properties of the transpose and the formula that I've written down, right? So it's clear this is a linear transformation. What do I know? I know that the kernel of L, right, is a subspace of R3 by 3, right? And what is the kernel of L? Well, the kernel of L here, it's equal to A in R3 by 3, right? Such that what? Such that L of A, which is equal to A minus A transpose, is equal to 0. So what is this subspace of R3 by 3 we're looking at?
Matrix minus its transpose equals 0. So, symmetric.
Yeah, right. So this is just a kind of wacky way of saying A such that A transpose equals to A, right? In other words, this is a very efficient proof that the set of symmetric matrices is a subspace. What's its dimension? Can you find a coordinate map? Right? That's the next question I'll ask. So that is a more nitty-gritty question, right? So let's see here how to say this. I mean, I could write it all out in terms of letters, but what's this say? This says AJI is equal to AIJ, right? For all IJ. Right? That's what that matrix condition means. And so there's 3 of those that are just kind of like, nothing being said. Right? Yeah, I mean, technically, there's how many equations there? 9. I suppose there's 9 equations. Is that right? Yeah, 9 equations, but 3 of those equations are really meaningless because A11 equals to A11, A22 equals A22, A33 equals A33. These are just tautologically true. So the equations here, which are not just kind of meh, are the ones where I and J are distinct, right? And of those, you'd think you have 6 equations, but that's where your heart might deceive you, right? Jeremiah 17:9, right? The heart is deceitful above all things and desperately wicked. Who can know it? This is probably not what the verse is talking about, but certainly there's a symmetry here in the indices. So like the 1,2 equation and the 2,1 equation, they're the same equation. So when you think about that, the 6 equations we had, ignoring the diagonal ones, there's really only 3. So when you distill it down, all you really need to think about is A12 is equal to A21, A13 is equal to A31, and A23 is equal to A32, right? That's pretty much it. And so if you look at it, if we take an arbitrary matrix A, right, we can write it as A11, A12, A13, A22, A23, A33, and I probably could have just written this and made a more convincing and quick argument. Like if you write this much of a symmetric matrix, you've written everything, right? Because once you specify above the diagonal, you're bound and determined to say what's below the diagonal, right? So, you have another class after this? Okay, good.
Only complex.
Okay, good. So I won't take too long because I'm still I'm still trying to get ready for complex. But anyway, it's just I'll let this finish where it finishes. All right. I'm not sure how long it'll take, but probably not much longer. So that's that, right? that is what an arbitrary symmetric 3 by 3 matrix looks like. And once you have that formula, and you have reduced the number of, you've eliminated any possible linear dependence amongst the parameters defining the object. Once you've done that, then you can just write out what you're looking at. You're like A11 times E11 plus A22 times E22 plus A33 times E33 plus A12 times E12 plus E21 plus A13 times E13 plus E31 plus A23 E23 plus A32. That is what we're looking at using the matrix units notation I introduced last time. And of course, in other words, A is an element of the span of E11, E22, E33. Goodness gracious. You know, if I was smarter, I would have put a plus rather than a minus in that map, because we would have gotten about the same out of it, and it would have been a lot less writing for me. Right? Because we could just as well change that minus to a plus, and then what we'd be looking at would be the anti-symmetric matrices, right? And what would have happened there is the diagonals would have been 0. So these would have been gone, and we would have just had differences rather than sums, and it would have been 3-dimensional rather than this, which is apparently 6-dimensional. So there you go. And definitely this is a spanning set for the symmetric matrices, right? And isn't linearly independent. It's clear that it's linearly independent from this formula up here. If you set this equal to 0, it forces all these coefficients to independently be 0. If you had tricked yourself into thinking you had a minimal set of parameters, right? If you check on the linear independence and you don't get linear independence, that's your hint. That's not a minimal set of parameters. There's something else I can fold in together, you know? All right, so now that we have all this, a basis is ordered, right? A basis is an ordered set. That's important. So if I call all this beta, then I can ask you, what is the coordinate map of A? And I'll make A something more fun, like A, B, C, D, E, F, G, H, I. There we go. So what would that be equal to?
It would be A, E,
Very good.
I,
Yep.
then 1, 2 plus 2, 1, that's A plus, sorry, B plus D,
Nope.
or
Nope.
D plus.
Mm-mm. So this is the tricky thing, is you can ignore these. It's just,
I see, yes.
so like it's just B, C, and then F.
Yeah.
And you see, if I was more kind to linear algebra students, I would write something like, find the coordinates of this. But I like to write the other thing to be a little bit more annoying. And my brother would just say something like, that's just bad math, like you shouldn't do that. He would say something like that. But I mean, of course, it makes my grading more complicated, because if I leave that as the D, if I leave the other letters down here, you know, then technically they could either put the B here, or they could logically put the D I had before, right? And you know, they'd have two choices of letters for these ones, because those are necessarily equal. That's the symmetry condition. So yeah, this is an element of R6, and so symmetric 3 by 3 matrices is a 6-dimensional subspace of the 9-dimensional 3 by 3 matrix space. If we were to look at the antisymmetric matrices, very similar calculation, we would find 3-dimensional subspace of three-dimensional subspace of our 3x3. Which means there's probably some kind of sneaky way to make like cross products in terms of matrix multiplication of those kind of matrices. Anyway, like there's so many things you can do with matrices. Let's see what I was going to say. We'll do more with coordinate maps, and I'll try to like look at the linear, like more about linear transformations, coordinate maps, how to change. How we'll try to look at change of basis next time. Basically, I think is where we are. Unless you have other things in the linear algebra you want me to look at, but. I would say this, there's another interesting thing to think about while we're on this example, which is like if we defined T of A equals to just A transpose instead of the one I did, but this linear map, then this space we're looking at, the space of symmetric matrices, is the eigenspace with eigenvalue 1. Whereas the antisymmetric matrices is the eigenspace of T with eigenvalue -1. And they form a direct sum decomposition of the 3x3 matrix space. And we could look at the matrix of T with respect to a basis for all of our 3x3 that's formed from the concatenation of eigenbases for the symmetric and the antisymmetric matrices. And we'd find that the matrix of T was block diagonal with like a 1 and a -1 down the blocks. We might run into that like next class or something. I don't know, but that's something I always ask about in homework because it's computationally simple, but it really forces students to think about the more abstract things. All right, enough.
Are you going to cover eigen?
Oh yes, we will. That is definitely on our list of things to go back over.
That's something I don't remember super well.
Good. Yes, we will go through the eigen stuff. But first, the coordinate change. Once we're done with coordinate change, the eigenvalue stuff fits naturally into there.
Okay.
Before even that, though, I need to talk about the matrix with respect to the matrix of a linear transformation and how we understand that with respect, how to define the matrix of a linear transformation, what that even means.
Sure.
That's what we'll do next time. So, but that